Okay, welcome everyone. So in this video, I want to connect our exploration of bases of subspaces back to very specific subspaces that we looked at for an m by n matrix A. Namely, we looked at the null space of A, the column space of this matrix A, and the row space of this matrix A. And we identified that all three of these spaces actually form a subspace of either the domain of this map or the codomain of this map. So either of Rm or of Rn. And so what I want to discuss now is how we can find bases for each of these spaces. So let's start with the null space. So recall that the null space of a m by n matrix A is going to be the set of all solutions x for the matrix equation Ax is equal to the 0 vector. So this is the homogeneous matrix equation. So let's consider an example. Let's take this matrix A, which is conveniently already in reduced row echelon form. You can verify that. So I have a pivot in column 1. We have a free variable in column 2. We have a pivot in column 3, a free variable in column 4, and then a pivot in column 5. And we have a last row of all zeros. And we want to find a basis for the null space of A. And just recall that the null space of A, that's going to be a subspace of the domain, since we're considering vectors that we map by A to the 0 vector. So this is going to be a subspace of the vector space R5. And our task is to find the basis for this subspace. So let's just recall what information we get from this reduced row echelon form of the matrix of coefficients A here and how they relate to this homogeneous matrix equation. So from the top row, we can see that x1 plus 4x2 plus 2x4 must equal 0. From the second row, we see that x3 minus x4 must equal 0. And from the third row, we see that x5 has to equal 0. And from the very last row, we don't get any additional conditions other than 0 equals 0. So we do have a consistent system. And because we have some pre-variables, this is not going to be unique. We have more solutions than just the trivial solution. So we take these equations that we identified over here from each of the rows of the reduced row echelon form, and we use this to write out the solution set. So I can say that any vector x for which x1 is equal to minus 4x2 minus 2x4. So we just bring these to the other side so that we solve for x1. x2 is a free variable. x3 has to equal x4 from this green equation that we found. x4 is a free variable. There's no pivot in the fourth column. And we see that x5 has to equal 0. So this means we can write this solution set as a linear combination as x2 times the vector minus 4, 1, 0, 0, 0, plus the scalar x4 times the column vector minus 2, 0, 1, 1, 0. So any x in our domain of R4, which looks like some scalar x2 times this first column vector plus some scalar x4 times this second column vector, is going to map to the 0 vector. So therefore, these two vectors that we've identified, they form a basis for this subspace, which is the null space of matrix A. So namely, a basis for the null space would be consist of these two column vectors, the first one being minus 4, 1, 0, 0, 0. The second column vector in this basis is minus 2, 0, 1, 1, 0. So here, we're really not using any new linear algebra constructs here besides what we've already looked at with null spaces and how we can identify the set of vectors that generate the null space. And so now we're just calling that set a basis for the null space.